Hello, everyone. Today we're going to start off by solving the classic Leet code question where we remove duplicates from a sorted list. So this time we are once again working with the linked lists. We're working with nodes, and then those go ahead and comprise the linked list. So if you haven't already done so, I do recommend watching these two videos, merging two sorted lists, dealing with singly linked list, and then also this one as well, merging two sorted lists. But this time, instead of using a deep copy, we're going to do it in place. The reason being is because in these examples, I go over what nodes are, how linked lists work, and just so that you feel comfortable with it. And then that way, if you already feel comfortable with it, you can continue watching. And if you don't feel comfortable with it, just know that you have that resource available. But going back to this problem, what essentially do we want to do? So we're given the head of a sorted linked list. So just think of it as a list, a sorted list like this, 1, 1, 2, or 1, 1, 2, 3, 3. And what we want to do is we want to delete all duplicates, right? So we want to make sure that each element or each value inside of our node only appears once. And we're using numerics in this case, but you could, do it with sorted strings, like if you put them in alphabetical order. So really you could do it with any data type. And then what we're going to do is we're going to return the linked list sorted as well. So we want to go ahead and prune or remove away all of the duplicates, and we want to keep it in sorted fashion. So for example, this list of 1, 1, 2, we want to go ahead and remove this duplicate. So depending on your algorithm, you could delete the first one, you could delete the second one. We'll talk about our implementation in just a second, but you'll notice that we remove one of the duplicates so that we're only left with 1, 2 distinct elements, right? Distinct values, I should say. Now, in this case, we could see that we're given a list 1, 1, 2, 3, 3. Now there's duplicates with the 1 and there's duplicates with the 3. But at the end of it, we should have distinct values. So we're going to have 1, 2, 3. This is going to be a very, very, very straightforward algorithm. It's a pretty straightforward problem. I think the only challenge is if you're not comfortable with working with kind of pointers, and then that's where it becomes a little bit of a challenge. I am looking to make a video on that perhaps at a later time, but just know that for this problem, make sure if you haven't done so already, feel comfortable with linked list. And then with respect to pointers, it might feel uncomfortable if you're not too familiar with them, but this first logic that we're going to perform, the pseudocode, is going to make you feel probably pretty comfortable. It's just a syntax that's going to be a little bit strange. So how do we work with these cases? What do we do? Well, essentially what we're going to do is we want to consider for some edge cases. So let's consider the edge case where our head is pointing to a null, right? So it's an empty list. There's nothing in it. And that's part of our constraints. It says that we can have 0 nodes up to 300 nodes, right? And as far as the values, negative 100 to 100, that doesn't really matter. But just know that we can have 0 nodes. So how do we address this edge case? The way we do this is we can have a while loop that says while we're going to have a current pointer that's going to point to the same thing that head is pointing to. So we're going to have two essentially pointers pointing to the same start point. The head is going to stay there. And the current, you could think of this as the way we're going to iterate or traverse our linked list. This is what we're going to use. You typically see this in a lot of implementations. So if it's pointing to null, so notice so by saying while current, we're actually saying while it's not null, right? Then we continue iterating. However, if it is null, as in this case, what we're going to do is we're going to break out of the loop. So because this is going to be false if it's pointing towards a null putter, and it's going to kick us out. So that's one way to stop, and that's going to deal with the whole edge case. The other way we can deal with another edge case is, what about the end values? So say, for example, or if there's only one value. So this happens whenever you only have one node in your list, or you have any node at the end of your list. So this is going to be very common, always at the end of your list, or if you have one node. So let's look at our head pointer. It's pointing to one node. And then, of course, whenever it's the last node, it points to no putter. So here we have a current pointer, which is also pointing to the start of, initially it's going to point to the start of our list. And what we want to do is, in order to check for duplicates, what we want to focus on is the current value and the next value. But there's an issue if my next value is null, right? If my next value is null, I can't really do any comparisons. Plus, it's not a duplicate at that point. So what we're going to do is we're going to consider it already sorted. So as you can see, it's already sorted. Not only is it already sorted, but it's also at the end of our list. So there's not really much more to do. You can kind of equate this similarly to when we were doing comparisons between the current value and the next value inside of a for loop. We always stop one short. We don't go to the very, very end. We go to one before the end. So that's when we set up our boundary conditions. It's the same thing here. When you're at the last node of the list, you just stop. You don't consider this. It's just because it's already at the end. So you just break out of the loop as well. And you'll notice here, so if our current next pointer is pointing to null putter, so in this case, then it's at the end of the list. So you're just going to go ahead and stop and break out. So those are two edge cases I just wanted to get out of the way. But what if it's continuous, kind of like this? So this is something that's more realistic or more probable. You could see that we have the values 1, 1, 2, 3, 3. And then since it's the last value, it's going to point to null putter. What we're going to do is we're going to set up we're going to go ahead and set up two pointers. We always set up current just because that's how we're going to traverse through our linked list. And then optionally, we can also set up, sometimes we're going to set up our next pointer. So this is also going to be a pointer just like current, and it's going to point to the node right after current. So this current is pointing to this node, next is pointing to this node. And there's really two options when we do our comparison. We want to determine, are these two values the same? If they are the same, we want to remove the next value. We want to go ahead and remove it. So to simplify it, it would look something like this. Yeah, just like that. And that would be our chain, right? We just removed our duplicate, right? So that's kind of a simplistic way of going about it. But just know we do have to perform additional steps just to make sure we don't have memory leaks. I'll explain it in detail, but just know that that's pretty much the basis of it. We just need to remove whatever the next was pointing to. The other case is when these are not duplicates. So say, for example, if we had this case, right, the 1 and the 2. So because they're different values from each other, what happens is we're just going to go ahead and say, well, that's fine. Since this value does not match the forward value, we're going to go ahead and just move forward, move our current forward. Okay, so that's all we do. If they're not, just move the current pointer forward. Move to the next node. Yeah. So that's what it means by here. Move to the next node. I know I used next node, so move. Maybe I should write it as move current to the next node, something like this. So it's a little bit better described. And that's really it. Those are the two options. So now I kind of want to describe in detail how it is that we're going to do this. Okay, because we want to look at our pseudocode and then we want to implement it in this example. So once again, so while our current pointer is pointing to an existing memory address, then we want to continue our loop. So this addresses that we don't get an empty list. Essentially, if there is an empty list, it'll help us with that edge case. Now, we also want to make checks that we're not at the end of our list, or if it's a single node list, then that'll help that case as well. And so if our current is essentially if the next node is equal to null putter, then we're going to go ahead and we know at that point that we're at the end of our list and we're going to stop. We're going to break out. So those are two edge cases we're going to take care of immediately. Now, if that's not the case, then we know we still have a valid next node. So we have two nodes right together. And so if they're the same as in this case, what we're going to do is we're going to set the current next pointer. So I put these in parentheses so that it makes sense. So the current's next pointer, also known as the next, so the currents. So this is currents, and we're going to set its next pointer, which is the arrow. You can think of it that way. So we're going to set this guy's arrow to the next node's next pointer. I know that sounds like a mouthful, but let's analyze what that means. We're going to set this arrow to the next node's, who's the next node? This node, his next pointer. So we're going to set this arrow to whatever this guy's arrow is pointing to. So we're going to set this arrow to essentially this too. Okay, that's all that we're doing. So once that's done, it's going to essentially do this. It's going to extract it here. We're going to paste it over here. And then you can see right here that that's it like that. That's all that it is. So we're just going and we're setting this guy's, the current's next pointer to the next node's next pointer. I know that sounds like a mouthful, but trust me, once you kind of visualize it, it makes a lot more sense. Now, technically, this next node, this next pointer is still pointing to this node. And this node is still pointing to the 2. So if I were to draw this more accurately in like a 2D model, it looks like this. It actually looks like this. So it's so here's the header, here's the current, and this is our stitched together list, just like you see it here. So 1, 2, 2, 3, null putter, 1, 2, 2, 3, null putter. And then here's the next node. You see how the 1 is no longer pointing to the 1, but it's pointing to the 2? That's what we wanted. However, I never went ahead and changed this node's next pointer. So this is also still pointing to the 2. But that's okay. We're going to get rid of this node in just a second. What we need to do as well, once we go ahead and do that movement, is we need to make sure to delete the next node. So this pointer has to delete this node object that lives on the heap. And that's because if we don't, then we get what's called a memory leak, right? So every time we create a node, we're doing it probably with DMA, dynamic memory allocation, so that it could have a longer lifetime. And until it's manually deleted, then it'll continue to persist, and it'll, so if you have memory leaks, it'll slow down your program and so forth. So what we want to do is we want to make sure we take care of this. And the way we do this is we go ahead and delete this object. So we delete the value and we delete this. And there's still an arrow that the next pointer is pointing to, but it's pointing to an invalid memory address. So we should probably set that to null, but it's a temporary, so it doesn't really matter. But you can see that it's gone now, and that's how we can get rid of the memory leaks. But that's really it. That's the whole process. That's the most difficult that it gets. If you have a match, if you have a duplicate. So what that would do is that would delete this object. And then that's it. Yeah, so that's pretty much it. Now, what happens if the current value and the next value, so let me go ahead and put next here, are different? If they're different, then all we need to do is move the current value forward. That's it. So just go ahead and move it forward. And in this case, again, if they're different, we're just going to move the current pointer forward. That's it. Now, in this case, if we have a duplicate, we're going to perform that trick once more. We're going to get the current next pointer. So we're going to get this arrow to point to the next node's next pointer. So that means we're going to go ahead and hopscotch, right? For those of you who are familiar with the game, we're going to go ahead and hopscotch this node and have it point to the null. So we're going to go ahead and remove this from here and put that off to the side by itself. Let's see. There we go. Just kind of get rid of some spacing. There we go. So it's all by itself. And then we're going to go ahead and delete this, right? We want to get rid of it, and that's it. And then now that we're at the last node, what case does this fall into? Now we're the last node falls into this case, right? So if if the current is pointing to null, right? If essentially the next node is pointing is null, then at that case we stop and we go ahead and break out. And that's it. All we need to do at that point, once we're done with this loop, so once we're done repeating steps 1 through 4, 1 through 4, 1 through 4, then it's as simple as just returning the head. And that's because the head is always going to stay at the beginning of the list. We always need a reference to our list so we know where to find it. We don't accidentally leak that memory. That's the straightforward implementation. I hope that makes sense. Please feel free to review this section. If it doesn't, definitely want you to feel comfortable with the implementation before, with the logic before the implementation. But let's go ahead and if you're finished with reviewing the problem, let's go ahead and start coding this out. So the first thing we need is we need a list node pointer called current, and it's going to point to the same. It's going to point to the same node as head. It's going to point, so both head and current are pointing, head and current are pointing to the same thing initially. And we're going to use current to traverse the linked list. Now, actually, let's state that. So we're going to start by pointing to same node as head. And we're going to point to this is always going to point to current node. We always want it to point to the current node. So we're going to use that for traversal. Okay. Now, the next thing we want to do is we want to set our while loop. So we want to say while current is, while that's true, and then this is gonna, so this is gonna say while current, so it's not null footer. This is gonna catch the edge case where we have 0 nodes. That's really only for the instance where we have 0 nodes. Well, it's actually going to allow us to iterate, but it's also going to be for the case where we have 0 nodes. So next up, we're going to have our if statement, and we want to check the second condition that checks if we're at the end of our list, right? So essentially, if the next node is equal to null footer. So if the next node, or my current, whatever current's pointing to, its next pointer is equal to null footer. So this is the last node of the list. Then we know we want to go ahead and exit because we're done, right? So we're done. There's no more duplicates. Essentially, if you're already at the end of the list, it's not possible to have duplicates at the end of the list, assuming that you're removing duplicates from the beginning, or you're removing duplicates as you encounter them. So that considers, or that kind of gets rid of our edge cases that we needed to think about. Now let's go ahead and do comparisons between the current value and the next value. Okay, so between the current node's value and the next node's value. In order to do this for convenience, let's set up some variables. And this is just so that we can use a little bit of less of pointer notation, so it doesn't look like we're using arrows everywhere. It seems a bit more comfortable. So what is the current value? Well, it's whatever the current pointers is pointing to, and we're going to go ahead and grab the data member value. And so we're using the operator to essentially dereference the object and then grab its data member. So this is the current value. And then how do we get the next value? Well, we need to have a pointer to the next value. So there's an easier way to write it if we just first create a pointer called, let's say, next node, and set it equal to current next, arrow next. So this is going to be the next node, yeah. So pointer to the next node, pointer to the next node. And the reason why we set that up is so that when we get the next value, well, in that case, we can use next node just like we did with the current node. So we're going to go ahead and say next node val, and then this is the next value. If not, then you would have had to say, right, so this would have been a lot messier. If not, this would have been, let's see, this would have been current next val, right? And that does not scream, kind of tidiness. That can get easy to like confuse, especially if you're not, maybe you haven't had your cup of coffee yet. So now that we have our variables set up, we want to check if there are duplicates. So what do we want to do in that case? Or actually, let's get to that. So how do I check if they're duplicates? We just say if the current value matches the next value. Okay, much easier to read. So are there duplicates? If so, remove the next node and then chain the list. Well, technically, we're going to chain list, and remove next node. So how do we do this? We're going to go ahead and, once again, just as a visualization, actually, where's that example? What we would do is we would get, like, how do we hopscotch? Back here. Let's say right here, if I want to hopscotch the two, I have to get the current's next pointer, and I want it to point to the next node's next pointer, essentially. That's what we're looking for. So let's go ahead and do that. So that's going to be the current's next pointer. So the arrow, this arrow, I want it to point to the next node's next pointer, whatever the next node's next pointer is pointing to. So we're going to go ahead and write that as next node. So we're going to hopscotch, I don't know if I'm spelling this right, hopscotch the next node. next node to chain current with, let's call it after, the one that's after. So that's how we chain them. Now the next thing we want to do is we want to remove, or we want to delete whatever the next node is pointing to, because it's all by itself. We don't need it anymore. We don't want it, but we don't want to have a memory leak. So we want to go ahead and delete next node. And then this is to prevent memory leaks, because of course we're going to probably dynamically memory allocate those nodes that were deleted. They were allocated with probably with the word new, so we have to manually delete them, unless they were created with some smart pointers. In that case, they're once they go out of scope, they'll clean themselves with the destructor. Then that's fine. But in this case, we're assuming that we're using manual memory management. So prevent memory leaks. And then, so that's pretty much as difficult as it gets. If there are duplicates, that's what we want to do. If there are no duplicates, so no duplicates, then what we want to do is we just want to move our current pointer forward. That's it. So go ahead and move it forward like that. That's it. So we're going to continue this loop. This is going to go ahead and continue until you get to the end of the list. Once you get to the end of the list, it's this condition which is going to break you out. Okay, so pretty straightforward. By the time we're done, so at this point, our head should have the list that was pruned of duplicates. So there should be no more duplicates. So we can just return the head. And that's it. So that's really our solution. I want to make sure by running this to double check that and make any syntax errors. So let's see what mistake I made. Member access with no pointer, undefined behavior. Okay, so let's look at this. I created the next node. Yeah, so at this point, I created the next node, which is pointer to the next node. Yeah, list node is equal to current next. Okay. And then int next value is equal to next node value. Seems fine. Let's read that error. So runtime error, member access with no pointer type list. Okay. Let's go back here. Just one moment. Just going to go ahead and take a second to troubleshoot this. So, current value equals current value. This node pointer. Next node equals current next, and next value equals next node value. Don't really see the issue. I mean, these are all publicly accessible. Yeah, this is a struct, so these are all publicly accessible. So is value this next node. This is list node pointer called next node, and it's pointing to the next memory address. So it's going to be the next node. Yeah. Let's see. Let's go ahead and take this. I don't know, maybe refresh or something. Not really seeing it. Okay, so while current. Oh, I see. Oh, I feel like such a rookie. I'm so sorry. So I just noticed on line 19, I don't check if it's equal to no putter, because that looked all right to me. It's just because I forgot to write an extra equal signs. I apologize. Thank you for your patience. Now that we go ahead and do that comparison, it should break if we're at the end of our list. There we go. Runtime accepted. I was wondering what was going on there. So the reason that failed is because it wasn't checking. It wasn't checking if we were at the end of our list. So because it didn't check if we were at the end of our list, it only stopped whenever we essentially got to our current to null. And so we started accessing memory that wasn't ours. because this helps us check when our neighbor, our next node, is null putter. And at this point, I'm starting to kind of dereference values, right? I'm trying to access memory, so I'm trying to dereference null, and you can't do that. That's undefined behavior. So that's the reason that that issue happened. Thank you for your patience. I really do appreciate it. But other than that, it's pretty straightforward solution, especially visualized. I think the only part that's a little bit complicated is when we hopscotch. But I hope that that made sense, at least the visualization that we performed. But please like, comment, share, subscribe if you enjoyed the content. Also, let me know what you think about linked lists and singly linked, or linked list, singly linked lists in this context, nodes in general. If you have any questions about that, or if you would like me to make a video on further describing certain aspects of any data structure, go ahead and just leave that comment below. I'd love to hear your opinions about that, and definitely up for recommendations. But thank you so much for watching. Really appreciate your time, and hope to see you soon.